single homework problem today. No more questions? No more?
So that I can control the hour. I'll be able to stay more engaged that way.
Okay. So we're ready to start with problem number 3. But before that, one could remind you that the homework assignment is due tonight. So if you have problems that you have not solved, please go ahead and solve them. So what's happening? Is the audio from...
No, all of the other.
Oh, somebody is not muted, I guess.
Well, they all are muted. This is a problem that other professors have been having with Zoom, with the OWL cameras.
Okay.
So we just turned down the volume of the OWL
Okay.
camera.
Okay, that will work. So if you have homework problems that you haven't solved yet, now is the last chance. So next week, we're going to start chapter 7, and I'm going to also be open to answer if you have questions about the practice test. So unlike the previous midterm, the practice test now is not going to be a midterm, but it is going to help you prepare for the midterm. So on the midterm, you're going to have questions from the homework assignments and from the practice test, and also questions that you have not seen before. But you have all the information that is needed in order to figure it out independently. So the midterm is going to be on Thursday at, what time did we say? 7 o'clock? 7 o'clock on Thursday. So at 7 o'clock, I'm going to email to everybody the questions, and you have 90 minutes to solve the problems, scan your solution, and email it to the email address that I gave with an email with my previous email. So the midterm itself is going to be shorter than the practice test, much shorter. So if you know the material, if you understand the material, you're going to be able probably to finish all questions and write them well in about 30 minutes. You have 90 minutes to do that. So since the time is limited, don't count on the fact that you can look at the question and after that you can open the textbook and figure out how to proceed. It just, in 90 minutes, it is not going to be possible. But if you know the material, you're going to be done very fast. You probably also want to make sure that you know how to scan the pages of your solution in a PDF, single PDF file. So you have to figure it out in advance, because sometimes technical issues happen, and you don't want this to happen during the test. Yes.
So does the test have to be done at that time that you're sending it out, or from when we open the file?
So the test has to be done by 8:30 on Thursday. So you, I don't have a way to know when you open the file. I'm just going to email the test, and you have 90 minutes after that. So
Is that at night? 8:30 at night?
yes. Oh, you want it in the morning?
No.
No night shifts here. This, yes.
What if we have another class at that time?
Well, if you have other class at that time, talk to me after class. We're going to arrange some different arrangement for you. Okay. Other questions? Maybe somebody from online. Okay, they want some problems, not too many problems actually, surprisingly. Well, that's good. Maybe all problems have been solved before. How many people are online again? There were six?
No, five.
Six,
because
five
one's
people
here.
with the, okay. Well, the attendance is not stellar. Do you have any suggestions how to increase the attendance? How to make this class more attractive and still do physics? Right, this is the trick. Well, if you have ideas, let me know. Yes.
Maybe we give brownie points every time we come.
Brownie points for attendance, but this would mean that we penalize people that do not want to come to campus. And there are people that have medical conditions, they don't want to risk it. And it will not be fair to penalize people. But again, people that are coming to class have the opportunity to earn brownie points. And also people that are online, they have the same opportunity, but they rarely use it.
What one of my other classes does to get people to attend at least the Zoom if they're not here is he does random quizzes. And if you're at home, you have to email it to them.
Random
During that
quizzes, well,
So
your
then you-
classmates are going to hate you for this.
I know. But like you get points just for doing the quiz and sending it during the class time so that they don't like try to watch the video later or not attend.
Yeah, well, maybe this may be a way to see it, but I don't want to make this class more stressful. Life is stressful enough, and making it more stressful by doing exams, quizzes. Every chapter I want to give a quiz, at least on the screen. And we never have the time because we do homework problems. So maybe, at least today maybe, if we finish the homework problems faster, maybe we can do some conceptual quiz type of questions. That's a good training and opportunity for everybody to get brownie points and to have some interesting discussions, hopefully. Okay, so let me continue now with the first problem, problem number 3 from the homework assignment. It is a problem. So this problem can be confusing because they don't give you too much information. They give you a single number, 39 watts, for this version of the problem, but they want you to figure out the answer. So let me remind you what we have so far in chapter 6. So we have a definition for kinetic energy of an object with mass m and speed v. We have definition for gravitational potential energy of an object that is with mass m and close to the surface of Earth. And we have total energy is only kinetic plus gravitational potential energy, just because we don't know any other types of energy. So only kinetic and gravitational potential energy is the total energy. We have the definition for work of a force was force times displacement times cosine of the angle between the force and the displacement vectors. And actually, probably the formula that is the only formula that we need from this chapter is the work energy theorem. It says that the work done by external forces, they say external non-conservative forces, is equal to the change of energy, change of total energy of an object. So it looks like nothing special, right? Keep in mind that change of energy, delta E, like always, it is final minus initial energy. So this work energy theorem doesn't seem very exciting and very important, but actually it is. So look what is going to happen if there are no external forces doing work on an object. In that case, this would be zero, the work would be zero, and you're going to have final energy minus initial energy is zero. In other words, final and initial energy of an object are equal to each other. So you have conservation of energy. Isolated system, no external forces. Energy is conserved. Energy cannot escape, it cannot come from anywhere if the system is closed, if the object is not in communication with external world. And for problem number 3, you need the definition for power generated by a force. So the concept of power in physics is quite different from the meaning of the word power in everyday life. But we just have to use the definition for power. So power of a force, power generated by a force, is the work done by this force divided by the time interval during which this work is done. That's it. Well, since very often the work energy theorem says that work is change of energy, you can interpret the power also as energy change per unit time. And once you know this, let's try to solve problem number 3. So they say that so you have some external force that accelerates a projectile from rest to certain speed v in certain time interval t. And the amount of power consumed by that force is given. For my version, it is 39 watts. They're asking how much power is needed to accelerate the same projectile from rest to double the speed in half the time. So look how to proceed. Of course, you continue just by looking at the definition for power. So the power that they give you for the first launch is going to be the change of energy of the projectile divided by the time during which this change of energy happens. So this is the power generated by the force that accelerates the projectile. Okay, so the first projectile, you have initial energy of the first projectile is 0 because the projectile starts from rest. And it doesn't have any height, it stays on the same height, the same level. Final energy of that projectile is 1/2 mv squared. Well, they don't give you the value of v, but they give you the letter. It has some value v. And now the power that they say is consumed during this acceleration is just, according to the definition, it is the change of energy divided by the time interval, right? So the change of energy is what? Final minus initial. Final is 1/2 mv squared, initial is 0. So the change of energy is 1/2 mv squared, and this has to be divided by t to give you the power for the first projectile. Well, do the same reasoning for the second projectile. The second projectile starts with energy. Let me clean here and let's do the second projectile here so that people online will be able to see. So the second projectile starts with energy E0 prime 0, right? Starts from rest also. And it acquires final energy equal to 1/2 the same mass, but now you want double the speed of that second projectile. So it is 2 times v everything squared. The power consumed for that acceleration is going to be, again, change of energy divided by the time interval. So it is going to be, again, 1/2 m 2 times v everything squared divided by, now the time interval is different. It is t divided by 2. And they practically are asking, what is this new power p prime? And to figure out this new power p prime, just take into account that when you modify this expression for p prime, you are going to get something similar to p, to the power for the first projectile, times some number. So in other words, try to modify p prime in such a way to get this expression. Well, it is not that difficult. You have 2 squared is 4. So you have p prime is going to be 4 times 1/2 m v squared. And now this divided by t divided by 2. Resist the temptation to do cancellations. You want to get 1/2 mv squared divided by t. And now using the rules for division of fractions, you can write this as 8 times 1/2 mv squared, all of this divided by t. So this t divided by 2, using the rules for division of fractions, this factor of 2 comes to nominator. And it becomes 8. And now here in the brackets, you have an expression that is exactly the same as the power for the first projectile. The power that you know, for my version, it is 39 watts. So the answer is going to be 8 times 39. Okay. Okay, let's see questions now. Okay, if no questions for this problem, let's go to problem number 5. Let's see what is problem number 5. Okay. So this is another problem. Actually, this is a problem that is easiest to figure out using, again, the work energy theorem. So you have this skateboarder that starts with some initial speed, and well, he's not exactly in a free fall, but part of the trajectory is in a free fall. They say that there is no air resistance and friction. So this means that, well, what are the external forces acting on this skateboarder? Well, in general, they could be friction, air resistance, but here you also have normal force, the force with which the ramp acts on the person. However, normal force never does work. And the reason is very simple. The normal force is perpendicular to the infinitesimal displacement. So here is, let's say, here's the trajectory, here's the person somewhere on this ramp. The normal force is perpendicular to the surface of contact, while the infinitesimal displacement for very short time interval is this way, along the surface. Therefore, the displacement and the normal force are perpendicular, angle between them 90 degrees, cosine of 90 is 0. And as a result, the work done by the normal force is 0. So this is always the case. Well, in that case, if the work done by external forces is 0, again, you have conservation of energy. And this is what you have to use to solve this problem. So here is the diagram for this problem. You have, here is the ramp, and you start from this point with initial velocity v0, and you end up at certain height above the ramp, and you have to find the length of this height. Well, again, use conservation of energy. Let's say that this is your initial point, and your final point, take it to be at the top of the trajectory. The energy at the initial point, well, first choose a coordinate system to be with origin at the launch point, at the initial point, so that the height and therefore the gravitational potential energy at the initial point to be 0. So in this case, the energy E0 is going to be purely kinetic energy, 1/2 mv0 squared. The gravitational potential energy at that moment is 0. And after that, what is the final energy? The final energy at the top of the trajectory of the projectile that is launched vertically upward, at the top of the trajectory for 1 instant, it is at rest. Therefore, the kinetic energy at the top of the trajectory is 0. and the object only has gravitational potential energy equal to this mg times this height. So it is mgh is the total energy at the top of the detector. And now, since the work of the external forces is zero, energy has to be conserved. Final is equal to initial. So you can say mgh has to be equal to 1/2 mv naught squared. You cancel the mass, and you get that the height that you're looking for is equal to v naught squared divided by 2 times g after cancellation of the mass. And this should be the answer. Let's see questions and remarks. Questions about this problem? Anybody? If not, let's go to problem number 8 from the homework assignment. Okay, so this is a biomedical type of question. Nutritional calories and so on. So it is again a problem related with the definition of power generated by a force. So they tell you that the power per kilogram of weight is 6.5 watts. This means that the power generated by the body of Lance Armstrong is given. It is 75 kilograms multiplied by 6.5. 6.5. And this power is going to be in watts, which is normal SI unit for power. So they're asking how much work does he do during a 125-kilometer race that is with in which he keeps average speed of 11.5 meters per second. Well, recall the definition. So they're asking how much work does he do, and just recall the definition for power. It is work done divided by the time needed to be done. In other words, the work that they're asking is going to be the power that they have given multiplied by the time interval during which this power is generated. How to figure out the time interval? Well, they give you the speed and the distance. So the time is just going to be the ratio of the distance. Make sure that that distance is not in kilometers, but in meters, divided by the speed. So distance divided by speed, this gives you the time, and that's it. So this is, once you do this multiplication division, you're going to get the work done by Lance Armstrong in joules. In joules, which is the SI unit. Now, to make the things quite confusing, in biomedical sciences, the unit for work and energy, often used unit, is a calorie. And to make the things even more confusing, there is a calorie with lowercase c, defined as the amount of energy needed to warm up 1 gram of water with 1 degree Celsius to 1 degree. So it is a small calorie is equal to approximately 4.2 joules. But in nutritional context, instead of calorie with small c, they use capital C calorie. And capital C calorie is 1,000 small calories, lowercase calories. So all nutritional labels are in capital C calories, kilocalories, capital C calories. And here, to make your work easier, they say that 1 joule is certain number of capital C calories. And part B, just multiply the number of joules that you got in part A with the conversion factor that they give you, and you're going to get the number of nutritional calories, capital C calories. What is interesting is that the answer is only 1,270 calories, which is the calories in one meal, let's say, or a Big Mac sandwich or something of that nature. So this has to be a little bit of a surprising result, because you're racing 125 kilometers with very high speed, actually. 11.5 meters per second is a decent speed, and you only burn this number of calories. So this doesn't seem to be very, kind of the right answer. But it is, because here we calculated the work done by this person if his muscles were 100% efficient. So all nutritional energy, all chemical energy in the food was converted 100% efficiently into work. In reality, this is not exactly the case. Like any other device, human muscles also have certain coefficient of performance that is not 100%. In addition to that, in addition to the work this person does, he also, his heart is beating, his breathing and so on. So there is a lot of additional work that is done in order to do the race. And as a result, 125 kilometer race, probably his body consumes much more than 1,270. Okay. Any questions or remarks? Yes.
I just went over my head, but how did you, like, what is time in that one for like the SB?
So the time is distance divided by speed. Distance is 125 kilometers. Make sure that you convert it into meters. And the speed is 11.5 meters per second for my version of the problem. So that's it. So this expression in the brackets is time. So well, 125. Well, calculate that time. I don't want to try to calculate it myself, but 125 kilometers, probably something like, no, maybe the time is going to be of the order of 4 hours, a little bit less maybe. What time do you get? So make sure that this 125 kilometers is actually 125,000 meters. The result is going to be in seconds. And when you divide that result into, the result is going to be in seconds. But it is going to be of the order of 4 hours. 4 hours, about maybe 11,000 seconds or something of that nature. Okay, other questions? If not, let's do some conceptual questions, and I'm going to project some conceptual questions for you on the screen. And for people that are online, we're going to project the same questions. Hold on. Let's see. Files. Okay, so we kind of did some of those questions before, explicitly or not. Let me put the same questions here. Yeah, go to documents, all quizzes, yeah, right there, 7, chapter 7. Yep, right there. And share the screen. Good. Excellent. So possible to do work on object that doesn't move? Clearly not possible because the formula for work requires displacement. Object at rest, 0 displacement. Okay, I don't remember if we talked about this question, but again, let's look at it this way. It's visible this way, right? But you also see the questions. Okay, here it is. A box being pulled across a floor, constant speed. What can you say about the work done by friction? Well, the work is going to be negative, right? Because displacement is in one direction, the friction force is exactly in opposite direction. So the angle between displacement and friction force is 180. Cosine of 180 is -1. Friction force does -40. Okay, now this question is one question that you may encounter. You have a ball that is going in a circular trajectory, and they're asking what is the work done by the tension force. The answer is exactly 0. And the reasoning for that is this. You have, exactly like with the normal force, here's the circular trajectory. Here is the object. Tension force is in direction, radial direction. This is the direction of the tension force. While the displacement for short time interval, infinitesimal displacement, is along the tangent to the circle. the tangent and the radius are always perpendicular from geometry, and therefore angle between them is 90 degrees. Cosine of 90 degrees is 0. And therefore the work is 0. Exactly like for the normal force, the argument that the normal force does 0 work is exactly the same. Okay, let's go to question. Next question is slide number 7. Is it number 7? Okay. You lift a book with your hand in such a way that it moves up at a constant speed. While it is moving, what is the total work done by the net force? So this is a tricky question, and the answer comes from the words that they are using. Constant speed. Well, constant speed meaning constant velocity, because you're moving along a straight line. Well, constant velocity means acceleration is 0. Acceleration is change of velocity. No change, 0 acceleration. But you remember Newton's second law says net force is mass times acceleration. If acceleration is 0, net force is also 0. If the force is 0, the work of that force is also 0, because the force is 0. 0 times anything is 0. So this is a tricky question, but important one. Okay, let's go to slide number 9. A car is traveling 60 miles per hour, and it can stop within 20 meters. What is the stopping distance if it is traveling with 120? Assume that the braking force is the same. Well, look, thinking in terms of work energy theorem, the work done by the braking force has to be equal to the change of energy of the car. Braking force is your external force. The change of energy, that the work of the braking force should be the change of energy. Well, the energy of a moving object is 1/2 mv squared. Well, if you double the speed, you have 1/2 mv double v squared. This means you quadruple the energy. So if this is 4 times larger and you use the same force for the work, the distance also has to be 4 times long. So this is the reasoning. This is kind of involved question, but it is almost not conceptual, but still you can do the argument the way I did it. So from 20 meters, the stopping distance is going to switch to 4 times 20 meters. Okay. So we have, let's go to slide 11. Slide 11. A car starts from rest and accelerates to 30 miles per hour. After that, it accelerates from 30 to 60, which takes more energy, from 0 to 30 or from 30 to 60. Well, this is a tricky one. And look, the change of energy, from 0 to 30 is final minus initial. Final is 1/2 mv squared. The initial is 0. So from 0 to 30, you have the amount of energy needed is 1/2 m30 squared. We're not doing SI units. We just want to compare miles per hour. The change of energy from 30 to 60 is final is 1/2 m60 squared. Initial is 1/2 m30 squared. Well, let's compare the numbers. So this is 60 squared is 3,600. 30 squared is 900. So the second acceleration from 30 to 60 is something of the order of 2,700 times 1/2 m. While the first acceleration is of the order of 900 only, because 30 squared is 9. In other words, acceleration for 30 to 60 requires more energy. You're going to burn more fuel than acceleration from 0 to 30. Surprising, you may not feel that when you're driving, you may not feel it, because how fast you accelerate depends upon the torque generated by your gearbox, and those things are not visible for you. But if you measure the fuel consumption, you're going to see that from 30 to 60, you're going to consume more fuel. Okay. We have time for one more question, I guess, right? So question 13, 2 blocks. The mass of the first one is larger than the other one. They slide, no friction, have the same kinetic energy when they hit a long stretch, which slows them down. Which one? And that one is a little bit. So in which case you're going to have. So this one you cannot answer without doing the arithmetic. You have to do the arithmetic for this one. So it's probably not a good question for a conceptual question, and I cannot think about shortcut to figure the answer. My guess is that, so the friction force is going to be larger for the more massive block, because the normal force is larger. But this larger force has to decelerate larger mass. So my guess is that when you do the arithmetic, the mass is going to cancel, and therefore the 2 blocks are going to have the same stopping distance. Oh, you get M2, I don't know. you have to do the arithmetic here. You cannot answer without doing the arithmetic, and we don't have the time to do it now. Oh, they're not asking about, okay. Okay. So this question is easy. Is it possible for kinetic energy to be negative? Look at the definition for kinetic energy. Mass is always a positive number. V squared is always non-negative, so you cannot get a negative number. Okay, so let's stop here. Everybody that is present in the class and all people that are awake online, please add yourself brownie point for those questions that we went over so far.